Good afternoon, students. On last round, we were discussing about phase lag network. Design procedure. Now, first we discuss design procedure for phase lag network. In first step, we draw the magnitude and phase versus frequency curve or Bode plot for uncompensated system. Then from Bode plot, second step, from Bode plot, determine the phase margin of uncompensated system. Third step, if psi s is the specified phase margin and this is the margin of safety, then given required phase margin or maximum phase margin or optimum phase margin is psi s minus available phase margin for uncompensated system plus margin of safety. Then from Bode plot, determine the new gain crossover frequency omega m, and corresponding to this omega m, we calculate from magnitude curve the magnitude of transfer function at omega m. From that value we calculate the value of a, and then from this equation we calculate the value of t, and when we know the value of omega m, a and t, we then find out the transfer function of phase lag network. Effect of phase lag network. For a given relative stability, the velocity constant is increased. There is a decrease in gain crossover frequency, thus decreasing the bandwidth, while in case of phase lead network, bandwidth is increasing. In phase lag network, bandwidth is decreasing. Phase margin increases, response will be slower. And in phase lag network, steady state response improves, while in case of phase lead network, transient response improves, and there is no effect on steady state response in case of phase lead network. Due to decrease in bandwidth, the rise time and settling time becomes larger. Then design a suitable lag compensator network for given transfer function. And the following required specification are kV is equal to 20 per second and phase margin should be greater or equal to 35. Then we calculate kV is equal to limit SGS as approaches to 0. This S is cancelled by this S and we get 25 K by 40. K is 800. GS is given by this expression, and we draw the Bode plot of this transfer function. First corner frequency is 2 radians and second corner frequency is 20 radians per second. And this is the observation table for plotting phase plot of Bode plot. And if we in last lecture I discussed this plot, so discuss the plotting of Bode plot. So this is the gain crossover frequency, and corresponding to this gain crossover frequency, phase margin is 0. And in this case, in this question, required phase margin is 40, and this 40 is corresponding to omega. Omega is equal to approximately 2 radians per second. Phase margin available from Bode plot of uncompensated system is 0. Specified phase margin is 35, and margin of safety is 5. So optimum phase or maximum phase is 40. And for this phase angle, value of omega is 2 radians per second. And at this value, at 2 radians per second, at this value, magnitude has value of 20 dB. So we substitute the value of magnitude of Gj omega, which is 20. 20 is equal to minus 20 log A. Value of A is 0. And value of omega m is 2 radians per second. So by using this formula, we calculate the value of T, which is 50. And so we can calculate the transfer function of phase lag compensator circuit, which is given by 1 plus A Ts divided by 1 plus Ts, and we get this. And overall transfer function after compensation is this. And then we draw the Bode plot of this transfer function. First corner frequency is this, second, third, and fourth one is this. This is the phase plot, and you can plot the Bode plot for this transfer function. Next question is, design a suitable phase lag compensator network for GS is equal to this, where kV is 30 per second and phase margin is greater than 40. As in previous question, calculate the value of kV, which is equal to K, and since value of kV is 30, so value of K is 30. And we can draw the Bode plot for this uncompensated circuit. This is the Bode magnitude of Bode plot, magnitude of Bode plot, and this is the phase curve for this uncompensated system. Okay. Then in this case, if this is the new gain crossover frequency, and corresponding to this gain crossover frequency, we get phase margin. This point is at 180, and if we calculate the value of this, we get phase margin is minus 22 degree, while desired phase margin is 40 dB, and this 40 degrees corresponds to omega is 1 to 3. When omega is 3, we get the desired phase margin and value of magnitude at when omega is 3 is 20 dB. From Bode plot of uncompensated system, phase margin available is minus 22 degree, required phase margin is 40, and this required phase margin for 40 degree is available when omega is 3 radians per second. And value of magnitude curve is 20 dB at omega is 3 radians per second. We substitute the value of magnitude of dj omega minus 20 log a is equal to 20 and value of a is 0.1. Then we calculate the value of t and value of t is 35.7. Then calculate the transfer function of the compensator is given by this, and calculation of overall transfer function is this. Then draw the Bode plot for this transfer function. First corner frequency is 10, next corner frequency is 5, lowest is 0.28, and this is 0.028. This is the phase plot. This is the phase plot, and this is the final or overall magnitude plot of overall transfer compensated transfer function. And in this case, we get the desired phase margin. This is the new gain crossover frequency, and this is the desired phase margin minus 180 to minus 140. It means that we get the desired phase margin at this omega value of omega n. Then compensation using root locus. When an improvement is required in steady state performance, a lag compensator is designed. The pole and zeros of lag compensator are placed in such a way that it does not affect the root locus carrying a dominant closed loop force. The first plot the root locus of uncompensated system. Means first step is to plot root locus of uncompensated system, then determine the value of k for for the desired damping ratio, and then obtain the dominant force. If steady state specifications are not met, design a lag compensator, and the pole and zero of compensator should be placed to the origin so that root locus remain the same. Design a lag compensator for a system whose open loop transfer function is given by this. First step, to draw the root locus of this transfer function. Design a lag compensator for a system whose open loop transfer function is given by this. So first you draw the root locus of this transfer function. Then for this damping ratio, determine the value of k. First you draw the root locus. There are three poles, no zeros. It means that there are three asymptotes which tends to infinity along asymptotic lines. Center of asymptote is sum of poles. Real parts of pole means 0, -1, -4 divided by 3. E minus z is equal to -5 by 3. Angle of asymptote is for 3 poles. Angle of asymptote is 60, 180 and 300. And for breakaway point, form the characteristic equation 1 plus GSHS is equal to 0. Then differentiate this characteristic equation with respect to S and equate dk by ds is equal to 0. You get the breakaway point. And in this case, breakaway point is minus is at minus 0.46. And point of intersection of locus with j omega axis is given by this characteristic equation. And from this Roth theory, we can calculate the intersection point of root locus with imaginary axis, which is plus minus 2j in this case. This is the root locus of given system. First pole is situated at 0, second is at -1, third is at -4, and since these are two consecutive poles, one breakaway point exists in between these poles, and this root locus tends to infinity, and this root locus tends to infinity along these asymptotic lines, and this root locus tends to infinity along third or symptomatic line. Clear? This is the root locus of this transfer function GS. Then for given damping factor means when damping factor is 0.5, cos inverse 0.5 is equal to 60. And so this angle, draw an angle from this negative real axis, and this angle is equal to 60, and draw this line. This line cuts the root locus at point A. Join this A point to this pole, next pole, and the third and last pole. Then measure the value of CA line, AB line, and OA line. Draw a line for damping factor 0.5, cos inverse 0.5 is equal to 60. Draw an angle 60 with negative real axis. Then measure the value of OA, AB, and AC, and value of K is given by multiplication of OA, AB, and AC. So we get the value of A 2.664. The velocity constant for the cascade system satisfied Kv is equal to limit S Gs of overall transfer function of compensated system. Means this is the original value of K is 2.664. So we put the value of K 2.664. This is the transfer function of uncompensated system, and this is the transfer function of compensated system, lag compensated system, and Kv is equal to limit S Gs. Gs is given by this, so Kv is equal to limit S multiplied by Gs, where S approaches to 0. Clear? Then this S is cancelled by this S, and substitute the value of S is equal to 0. We get this equation, and here we calculate the value of A is equal to 0.13. The lag compensator should be placed so that root locus is not disturbed by putting compensator pole and 0 near the origin, because compensator always add either 0, either not 0 and 4 to the original system. So this lag compensator should be so placed that the root locus is not disturbed by putting the compensator pole or 0 near the origin. Generally, 10% of the distance between origin and the first pole on the negative real axis is taken as a location of compensator 0. Location of compensator 0 is in between 10% of origin and first pole on the negative axis. So we can say that 0 is location of 0 is given by minus 1 by AT is equal to minus 0.1. So A is, we get the value of A, and we know the value of A is 0.13. So we get the value of T, and from getting the value of A and T, we form the transfer function of compensator system. Distance between origin and first pole is 1. So 10% of 1 is 0.1. So this minus 0.1 is the location of 0. So here we calculate the value of t and get the transfer function of phase lag compensator. In next question, we will take 5 minutes break now. Next question. Design a lag compensator for Kv is greater than or equal to 5, damping is 0.707 and omega m is equal to 2 radians per second. Transfer function of uncompensated system is given by this, and root locus of this transfer function is 1 and 0. First pole is situated at 0, second pole is at -4, and third pole is at -5. There are three asymptotes, 60, at 60, at 180, and at 300. Clear? And -1.4 is the breakaway point. So this branch break away towards infinity along asymptotic line. This is the root locus of this transfer function. Then in the question, damping ratio is given by 0.707 and omega is given by 2 radians per second. So we draw an angle with negative real axis, and this angle is given by cos inverse 0.707, and this angle cuts root locus at point A. Then measure the value of AC, BA, and 0A. And when we multiply these three distances, or we get the value of K by multiplying 1.33.2 and 4.1, and we get the value of K, which is 23.6. Then Euler constant for cascade system should satisfy this. Kv is equal to limit s approaches 0 s. This is the transfer function of compensated lag compensator, and this is the transfer function of uncompensated system. So we calculate the value of A for overall transfer function and take the distance 10% of the first pole from the origin, and first pole is at -4 from origin. So 10% of 4 is 0.4. Value of A is this. Then we calculate the value of T, and from value of T and A we get the transfer function of compensated system. Then next is lead compensator. Draw the root locus of given open loop transfer function. Then from transient response specification, determine the desired location of dominant closed loop poles, which is given by this minus beta omega n plus minus j omega n under root 1 minus beta square. Next and last question is, for a system shown above, design a lead compensator such that omega n is 4 radians and value of damping ratio is 0.5 for compensated system, and this is the original system. Draw the root locus for this and determine the or plot the dominant closed loop poles at the desired location, and desired location is given by this formula. Substitute the value of zeta and omega, and in this formula we get this is the desired location of dominant closed loop pole. Okay. Jaya, have you any problem? Hello, Jaya, Avantika. Um, this is the root locus. First pole is at 0. Next pole is situated at -2. And this is the root locus of given system. Okay. And this is the desired. This is the desired dominant pole. From this point, we draw a line parallel to the x-axis and join this point to the origin. Clear? Then bisect this total angle, and this is the bisector line. This is the bisector line, and here we calculate the desired phase angle. This pole draws 90 degree at this dominant pole, and this pole draw 120 degree at the dominant pole. So we calculate connect all the poles to the point P and then find the angle of deficiency. And angle of deficiency is 180 minus 90 plus 120 is minus 30. Similarly, we get here this minus sign is replaced by plus sign, and we get in this case we get 30 degree. So lead compensator must contribute 30 degree at this at the at this point. ठीक है 30 degree. So we draw a line parallel to the x-axis and join this and then bisect this angle. This is the bisector angle, and angle of deficiency or is 30 degree. So we draw a 15 degree in this direction and 15 degree in this direction and join these two lines on this pole. And this is the location of 0 and pole of the compensated system. From the plot, this is the location of 0 and this is the location of pole. Avantika. Why we take this is the location, why we call this is the location of 0 and this is the location of 4. Avantika, Jaya, Charu. हाँ, I'm asking why we why I say that this is the why I'm saying that this is the position of 0. Avantika, Jaya, Charu, Charu, Shubham, Avantika, tell me. Then 1 by t is 2.96 and 1 by at is equal to 5.5, and so we calculate the value of t and alpha, and when we substitute the value of t and alpha we get the transfer function of phase lead compensator. Charu, Shubham, so time is over.